Hi there, this is the companion video to the TC66 review you will find on my channel, link in the description. It doesn't repeat that material, so if you have not seen it, watch it first and then come back to this one if you like more details on USB Type-C and the INA226 chip. However, be warned that it's going to be rather dry. Let's have a super quick tour of some aspects of USB Type-C. Don't worry, I won't bore you to death with a full 373 pages of the standard. I only touch on what is needed to understand the TC66. In USB Type-C, you come across three basic kinds of devices named after where they sit in a USB Type-C connection. They are called downstream facing port or DFP, upstream facing port or UFP, and dual role data or DRD. Ports here refer to the USB Type-C connector. Examples for each you can see on the right. Downstream is the source of data or power or both, while upstream is the sink of power or data. The DRD sits in the middle as it can do both. The DFP can only deliver power and no data, as in a charger, or it can only provide data, as for example a desktop PC, or it could do both, and similar nuances can be found for UFP and DRD. A DRD has to be able to play either the role of UFP or DFP, so I concentrate on those and I won't be mentioning DRDs any further. Let's add some color to the discussion, an idea I took from a presentation published by Texas Instruments. The top is the USB Type-C socket with its two rows of 12 contacts. It is colored according to functions. We have power in the form of the green and red colored ground and V-bus pins and the center D+ and D- differential pairs in blue, which are present in all earlier USB standards. On the left are the TX1 plus and minus and the RX1 plus and minus super speed differential pairs in yellow and orange that USB 3.0 and 3.1 uses. New for USB Type-C is a second set of super speed differential pairs RX2 plus minus and TX2 plus minus on the right, and of course the configuration channel pair CC1 and CC2 and the sideband use pair SPU1 and 2, all shown in white. Below the socket is my depiction of the USB Type-C plug using the same color scheme. Note that the plug has no contacts for the upper D+ and D- pair. As you know, the USB Type-C plug can be reversed or flipped as it's called in the standard, and if you imagine that the lower picture of the plug is moved over the socket above, you can see how this is achieved. The ground and V-bus lines match up, and therefore the USB Type-C can use 4 parallel wires for carrying V-bus and ground, which explains how it can sustain up to 5 amps of current flow. In this orientation, the plug and the CC pins, SPU pins, as well as the 2 super speed pairs all match up with their counterparts in the socket, and the standard D+ and D- differential pair in the plug aligns with the lower set of the D+ and D- contacts in the socket. If the plug is flipped, you can see that the power connections still line up, but in this orientation of the plug, the CC pins, SPU pins, as well as the 2 super speed pairs are reversed. So TX2 connects to TX1 and RX2 to RX1 and vice versa. But the direction, transmit or receive, is maintained, as is the polarity, plus to connects to plus and minus to minus. The standard D+ and D- differential pair in the plug now connects to the upper set of the D+ and D- contacts in the socket, and again polarity is maintained, plus to plus and minus to minus. The sockets now have a problem in that the data for the first super channel flows through the pins of the second super channel in the plug. This can't work, especially if there's only one super channel for USB 3.x. Therefore, the sockets need to establish what orientation is in use and, in a case like this, switch or multiplex, as it's called in the standard, super channel 1 transmit and receive signals to actually use the socket super channel 2 pins. The same multiplexing is needed for the D+ and D- signals to make sure the socket uses the ones that are actually wired in the plug. You can see this gets complicated. To make life a little easier for dumb devices like chargers, where the socket doesn't implement any data, or a USB 2 device that has no super speed data to offer but likes to use a Type-C socket, the standard allows the socket to connect the D+ and D- pairs with each other. The reason why that's possible is because the plug only contains one pair of D+ and D- contacts and the data speed is slow. If you would try such a thing with a device using a single superspeed channel to avoid the effort of switching, the resulting reflections would ruin all the data exchanges. So how do sockets find the plug orientation? That's where the CC or configuration channel comes in. The principle is quite simple for a change. The DFP uses the RP resistors to pull its CC pins up, while the UFP uses the RD resistors to pull its CC pins down to ground. Initially, the DFP just powers its RP resistors. V-bus is turned off, so quite different to older USB standards, by default there is no power present on the USB Type-C connector until a DFP knows that a UFP is connected. This is to prevent two DFPs trying to force power into each other, which would only end in tears. If a USB-C cable is connected, let's say it's flipped, this is what happens. The DFP monitors CC1 and CC2 lines and detects that they are pulled down by the UFP. It actually waits a bit to debounce the plug insertion, and there are other details over which I gloss over. It then picks one of the CC lines, the one that corresponds to the way its first superspeed channel would naturally use the connector pins. In my drawing it picked CC1 to use TX1 and RX1 as the first superspeed channel. It disconnects RP from CC2 and turns V-bus on. In addition, if the DFP detects the low ohm resistance of an RA on CC2, it assumes that this is an active cable with a built-in chipset and turns on VCon on CC2 to power it independently from V-bus. The VCon supply is done via a diode that I don't show here to prevent backfeed in case the UFP also powers VCon. In the meantime, the UFP was monitoring V-bus, and since it's now active, looks at its CC1 and CC2 lines to determine the configuration. It detects that only CC2 pin is still pulled up by RP in the DFP, so that pin carries the CC signal, which means it's a flip connection. The UFP configures its multiplexer to reroute the first superspeed channel to use TX2 RX2 pins instead, and of course the second superspeed channel would now use the TX1 RX1 pins. Not shown, but the same mux switching happens for the pins using the slow USB 2 D+ and D- channel because the plug does not connect them in a flip connection. If the UFP detects RA on CC1, it can provide, via a diode, VCon as well to power any active circuitry in the cable. DFP and UFP now exchange messages on voltages and currents via the CC wire using the USB PD or Power Delivery Protocol. You may think now that the DFP doesn't need a mux since it can choose suitable configurations, but that is not always the case. If the UFP is a device with a permanent attached cable and a USB-C plug like some docking stations, or like the TC66 has a built-in plug end, then because of the missing D+ and D- contacts on one side of the plug, the device configuration is predetermined. In fact, such a UFP does not need or implement mux circuitry. In this case, it's a DFP that needs to adjust to a possible flip connection as shown in this diagram. In the TC66 case, the fact that one end is a fixed plug means that flipping the cable connector on the other, the TC66 socket side, does not work because it can't respond to a flipped CC. A quick word about VCon. It is used in high-end USB-C cables to power electronics that are embedded inside the cable, actually in the plugs on either end. The purpose of these active cables is to sometimes improve signal quality on the superspeed channels. It enables longer cable length, but mostly to deliver more current. If a cable can carry more than 3 amps, up to 5 amps is possible, it must use additional chips in the plugs to exchange messages over the CC lines with the sockets, identifying itself and confirming its high current capacity. Without active circuits in the cable, only 3 amp current is possible. And talking about current capacity, I want to end the fast tour through the wonders of USB Type-C with this picture from the standard. It shows a legacy adapter for charging with a USB Type-A connector on the left and a USB Type-C connector on the other. You see that it contains an RP resistor to signal the necessary configuration to the USB Type-C end. In addition, because older USB standards don't have a configuration channel to exchange messages, the value of the RP resistor defines the allowed current the USB Type-C end is allowed to draw. The table specifies the already familiar 56K plug resistor RP as default, which coincides with allowing for 500 mA current draw. There are other values of RP, and using a 10K resistor, for example, you can allow 3 amps of current. The standard is clearly not condoning this practice. It says here that the value of RP shall use the default because while the adapter cable may be able to handle 3 amps, the cable does not know the capability of the charger, which may be overloaded by a USB device believing the fake advertised current capability. Here's one of those that is USB 3.1 compatible, but the pack does not say a word about that this cable will always advertise 3 amps current availability. I cut it in half, and while the superspeed channel wiring looks reasonable, the red V-bus lines seems just about capable to carry 3 amps. With a little USB-C breakout board, more about those in a moment, it's easy to find there's a 10K resistor between V-bus and CC buried in the plug. This dilemma of buried resistors in plugs and other cable wiring oddities made my investigation of the TC66 really hard. The trouble is that the tiny USB-C contacts are impossible to probe directly, at least for me, and after getting confusing results using various adapter cables, I decided to buy some breakout boards. This is the one you have seen earlier. You can buy it cheaply on eBay, but I don't recommend it. It doesn't break out any superspeed channels, so it's really only good for power delivery, but its labeling is very confusing and plain wrong in places. Initially, this was the only one I had, and none of my measurements made any sense. I then bought this one, which is brilliant. It gives you access to all 24 socket pins without adding confusing labels or resistors. The only small inconvenience is that half of the contacts are on the underside, making probing inconvenient, but you can always flip the connector so the signals on the top and underside switch places. Good universal breakouts for plugs are harder to find. This one is from Pimoroni. Unfortunately, it adds labeling, which is only correct if you don't flip the connector. It also comes with a 5K1 RD resistor installed. This one you can easily remove, as I have done on one of the boards. The board also allows you to add your own choice of RP if you wish. Let's talk about the INA226 for a moment. I've used an earlier variant, the INA219, in one of my own projects, the power monitor, link in the description, so I'm quite familiar with it. The fact that the designers of the TC66 have chosen that chip is really very good news for more than one reason. Firstly, this is a chip that was especially designed to measure voltages, current and power with very high precision, and secondly, because all the measurements are basically done by the chip, its datasheet gives us so much more details on how the TC66 works that would never be available if this were all done in the TC66 firmware using the ADC in the microcontroller instead. As you can see, the INA226 allows the designer a choice to put the shunt either on the high or the low side. High means on the voltage supply side of the load, while low means on the side where the load is connected to ground. Both ways have their advantages and drawbacks. The INA219 in my project only allowed high side, and in fact the TC66 designers also use high side, so I modified this diagram a little to reflect that design choice. What we have here is a delta sigma analog to digital converter, or ADC, that can be switched electronically between measuring V bus voltage when the switch is in the V position and the voltage drop across the shunt resistor if the switch is in the I position. The switching happens automatically, and in each cycle the chip takes a V measurement, then an I measurement, converts the shunt voltage to current value using the shunt resistor value and Ohm's law, and then calculates the power by multiplying voltage with current. The conversion time spent by the INA for taking each sample can be selected in a wide range, and it's also possible to select averaging of values. This has mainly the objective to reduce noise as shown here, because there's a hard limit of the resolution you can get out of the INA226. The least significant bit of the 16-bit registers for the bus voltage and shunt voltage are fixed to be 1.25 millivolts and 2.5 microvolts respectively. For the bus voltage, which can only be positive, that translates to a theoretical maximum of just below 41 volts. Of course, the max allowed voltage for the INA226 chip is just 36 volts. Of course, the firmware can implement its own oversampling of the INA registers and thereby improve resolution. For example, with a conversion time of 1.1 milliseconds and 256 times oversampling, a high-resolution bus voltage with 0.1 millivolt resolution would be available every 282 milliseconds. For current, it's not quite so easy to determine what's going on. The INA chip has an elaborate process to calculate configuration register values that enable it to convert shunt voltage into current and then current and bus voltage into power. It is too complex to go into details here, but one of the limits is that it must all work with integer values because of the limits the way the INA226 does calculations. It turns out that the choice of a 0.015 ohm shunt makes things tricky because 0.015 is 3/200 and the best config value I could find that satisfies the integer requirements is resulting in a very odd current LSB of 0.66666 milliamps or 1/1500. There is of course another way, which is that the firmware simply reads the shunt voltage register and calculates the current itself, instead letting the INA chip do it. This frees it from the math and configuration constraints of the INA chip, but it also means that neither power calculation nor the threshold alarms provided by the INA chip work anymore. The TC66 doesn't use alarms, and if the firmware calculates current, it can surely calculate power as well. Using this method has the additional advantage that, as for bus voltage, the firmware can use oversampling to improve the shunt voltage resolution, which is a lot easier than trying to do that with current. So, on the balance, I'm pretty sure that the TC66 uses shunt voltage directly and calculates the current itself instead of using the INA chip. Either way would result in the same maximum current of plus minus 5.461 amps. To verify that, I ran a test using the TC66 micro USB port to record the values when I ran up the current over 15 seconds from 1 amp to 5.8 amps and down again, holding my breath not to damage anything, pumping 20 watts through that poor thing and my stressed USB connectors. You can see how the voltage collapsed because of the resistance of wires and tracks, but the main thing I wanted to see is this current peak with a flattened top. All recorded values on a peak were exactly 5.46579 amps. The difference to the theoretical value is less than 0.1%, well within a tolerance of the shunt resistor, which might not be exactly 15 milliohms as I used in my calculation. Any variance of the real-world shunt would have been compensated for by using either the calibration registers in the INA226 or a correction in the firmware. After resolution, let's talk about errors. Here are some of the core specs from the INA226 datasheet. Some of these we already discussed, such as the shunt and bus voltage ranges and the least significant bits for both. There are two main sources of errors that will affect any measurements done with a current sense amplifier like the INA226. The first one is the gain error, which is typical 0.02% but could be as high as 0.1%. This means the measured value will lie between 0.02% and 1% of the actual value. Crucially, because the gain error is a percentage, it stays the same regardless whether you measure a very tiny or a very large value, as long as the temperature doesn't change. More problematic are the offset voltages for shunt and bus voltages, which are absolute and add or subtract to the true value measured. Naturally, the error caused by a constant offset increases dramatically the smaller the actual measurement voltage is. To illustrate the point, here's a plot of the theoretically expected bus voltage accuracy based on the datasheet offset of typical 1.25 mV in blue or the maximum offset of 7.5 mV in red. The graph below enlarges the area from 0 to 0.5 volts. With a positive offset, the lower the bus voltage gets, the higher the error. Of course, the offset could as well be negative, in which case the curves would be mirror images and the error dropping towards negative infinity instead. In the hope that the INA226 in my TC66 is typical or better, the error caused by the offset should be below 1% of voltages above 100 mV and below 0.1% for voltages above 1 volts, but worst case, it could be as high as 7.5% and 0.75% instead. The same calculation for the current using the shunt voltage over the shunt resistor of 15 milliohms as used in the TC66 shows a similar picture, but it's not as severe because the INA226 offset for the shunt voltage is amazingly small and the current shunt resistor is relatively large in comparison. This means the voltage drop created by the current flow across the shunt, even for small currents, is already high compared to the tiny offset. For 10 milliamps, the voltage drop is 150 microvolts, so an additional 2.5 microvolts based on a typical offset causes only an error of 1.67%. Of course, if the offset is the maximum of 10 microvolts, the error would be much higher, almost 7%. With that knowledge, it's time to look at the specs of the TC66 taken from the manual that you can download from that website here. The first thing to notice is that the voltage measurement range starts at 5 mV and not at 0. In light of the INA226 offsets I just explained, this makes sense. With a 1.25 mV typical offset voltage, no meaningful results can be expected at those low voltages. The next thing is the claimed resolution of 0.1 mV. Since we know the least significant bits from the INA226 chip is fixed at 1.25 mV, the TC66 firmware obviously oversamples, and as discussed, an oversampling rate of 256 would get it there and complete well in time for the 2 Hz update cycle. It's the same for current, provided the firmware oversamples the shunt voltage. So the claimed resolution for both is theoretically achievable, but whether they do in practice remains to be seen. Another question is whether the accuracy is sufficient for these resolutions to make any sense. So let's have a closer look at these accuracy claims first. It uses the common notation of a percentage followed by a number of digits that are uncertain. Here's a quick explanation of what 0.05 plus 20 digits and its equivalent statement for current really means. Let's say we have 5 volts, the accuracy is 0.05%, the resolution is 0.1 mV and the digits is 20. These highlighted values are all from the TC66 spec. The 0.05% accuracy means the actual voltage can be 5 volts plus or minus 2.5 mV. The 20 digits figure means the value we see on the display could be up to 20 digits more or less than what is shown. At 0.1 mV as place value for the last digits, 20 digits means 2 mV. The worst case is both the error from accuracy and the digits uncertainty add up, so when seeing 5.0000 on the display, we could really be measuring 5.0045 or 4.9955, and the device is still in spec. This translates to an actual error of 0.09%. It is interesting to see how the two parts of this accuracy statement, the 0.05% and the 20 digits, play at different voltages. The digits part is fixed because it only depends on the resolution, which is a constant 0.1 mV in the TC66, which means 20 digits is a constant 2 mV error term. Its effect is analog to the offset value in the INA226, in that the effect on the error gets larger the smaller the measurement value is. This plot shows for 100 mV, the error could be as high as 2.05% and we would still be in spec. The higher the voltage, the smaller the effect of the 2 mV digit error term, and now that 0.05% accuracy becomes the dominant factor. This is why at large voltages the error approaches but never quite reaches, let alone drop below the 0.05%. Exactly the same happens for current. At 1 amp, with a stated accuracy, resolution and digits, we have an effective 0.13% accuracy. At 100 milliamps, this has grown to 0.4%, and at 5 amps we get close to 0.1%. If you recall, these curves look a lot like those we have seen when analyzing the offset errors on the INA226, and I think the chip makers of the TC66 have simply used the digits term to express their experience with gain and offset errors using this chip. If you look at this way, 20 digits on the voltage is equivalent to 2 millivolts, and we know the INA226 V offset for V bus is typical 1.25 but could be up to 7.5 millivolts. Same for the current. 30 digits means 300 microamps. Over a 15 milliohm shunt, that is 4.5 microvolts. The INA V offset for the shunt voltage is between 2.5 microvolts, typical, to 10 microvolt max. In both cases, the stated digits represent a conservative middle ground they are confident with, probably based on measuring many devices. I have already covered the voltage and current plots in the other video. Here I want to get into more details on the behavior at low values, where we get into the effects of the offset voltages of the INA226 on V bus and V shunt, and of course resolution, because accuracy and resolution are different things. These graphs zoom into the range from 0 to 500 millivolt. As you can see on the raw data graph on the left, these kind of plots always suffer from the problem that the smaller the values get, a single-digit difference between the adjuvant and the TC66 results in an increase in error percentage and causing an increasingly spiky graph. So it's necessary to use some kind of smoothing, like a running average filter on the right, which reduces the problem at least somewhat. Despite the graphing problem, it is pretty clear that we can measure with 0.1% accuracy down to 150 millivolts and further down to 50 millivolts, still with at least 0.25%, which are excellent values. To get an idea of the resolution, I ran two tests where I increased the voltage by 100 microvolts on the left and by just 10 microvolts on the right. Both graphs plot the voltage of both the 34401A and the TC66 at just over 5 volts. At a 100 microvolt step size, the TC66 follows the 34401A closely and much better than it would if it had only a resolution of 1.25 millivolts, so some serious oversampling must be going on here. Looking at the graph on the right, 10 microvolt steps are definitely below what the TC66 can resolve, and it can only show the closest 100 microvolt values. For both graphs, I include a linear trend line for the TC66, and it matches the 34401A closely. Good enough to conclude that the claim of a resolution of 0.1 millivolt is true. You might be surprised about the rather large difference between the TC66 and the 34401A plots, but this is because of the large magnification. The measurements are really down into the weeds, and despite appearance, the error between them is still only 0.01%. For me, resolution of the current is much harder to verify than that of the voltage, because it's quite difficult to produce really fine current steps on a current that is sufficiently high to stay clear of any offset errors. The best I was able to do is this graph. It shows a current of about 80 milliamps that are increased in 100 microamp steps. At a current of just 80 milliamps, the error caused by the INA shunt offset voltage is certainly noticeable, and it's between 0.2 and 0.25%. The main point is, however, that the TC66 current closely tracks the 34401A, which means it has a resolution of at least 100 microamps, instead of either 666 microamps using the INA current register or 166 microamps using shunt voltage directly, both without oversampling. It looks as if it might well be 10 microamps, but I can't verify that with my means. The last parameter to discuss is resistance. With that I mean input resistance for measuring volts, which should be as high as possible, and shunt resistance for current, which should be as low as possible. The latter is usually expressed as burden voltage. To input resistance first. For these two plots, I use the BM869S to measure the input voltage into the TC66, while the Agilent 3441A measures the current. Note that both plots use logarithmic scale for the y-axis. In the plot on the left, the TC66 was powered from the micro USB port and PWR switch was off. It shows the input resistance against input voltage, and you can see it quickly settles to around 200k and then gradually increases to more than 400k at higher voltages. Doing the same measurement with PWR on and not powered from micro USB reveals a very different behavior. Up to just above 3 volts, the resistance is very high because the TC66 is essentially dead. It then boots and the resistance falls to 200 ohms. With increasing voltage, it gradually increases, but the best is just over 1k. This is of course no surprise, as the TC66 is taking the power it needs for operating from the measurement itself. The externally powered TC66 behaves much better and imposes only a very small extra load on the measurement. Of course, 200 to 400k is still quite a bit lower than the 10 meg ohm that a standard multimeter has these days, but it's certainly usable. On the burden voltage, the TC66 has only one range, so its burden voltage stays the same regardless what you measure. 0.015 volts per amp means that at 1 amp current, the TC66 loses just 15 millivolts. At 100 milliamps, only 1.5 millivolts, and so on. Compared to my other meters, this is an excellent value. The next closest in terms of burden voltage is the Pimoroni BM235, dropping already 40 millivolts at 1 amp and 190 millivolts at 100 milliamps, but its resolution is orders of magnitude less than the TC66. As you can see, the voltage drops increases further down the list. On most multimeters you can trade burden voltage against resolution. For example, if a drop of 330 millivolts is unacceptable when measuring 100 milliamps on the BM869S, I can always use the 5 amp range instead of the 500 milliamp, and the burden voltage for 100 milliamps drops to just 4.5 millivolts, but that means I lose 1 digit of display resolution. The TC66 with its single range does not allow this trade, but then it doesn't need to. Its 1.5 millivolt loss for 100 milliamps is still 3 times less. You will probably sigh in relief because we have finally reached the end of the additional material on the inner workings of the TC66. Thanks for your patience, and don't forget to subscribe and maybe become a Patreon. Details are in the description of the video. Thanks for watching.